Hello, in this video we will be looking at parametric integration. So the general formula for integrating between x equals a and b is as shown, the integral of y dx with limits of a and b. When we need to integrate a curve defined parametrically, we need to use expressions therefore for y and for dx, as well as, if we're doing it in terms of t or theta, we need to change the limits from x equals a and x equals b to whatever the corresponding values would be for t or for theta. To find an expression for dx, we can do that as we have in the past with substitution, for example, by differentiating x with respect to t or theta. So we're going to look at two examples. The first one with exponentials. Find the area of the region bounded by the axes and the curve defined parametrically as x equals 3e to the t minus 2 and y equals 4 minus e to the t. And so it's a good idea, of course, to know what we're actually looking at. So here is the graph of x equals 3e to the t minus 2 and y equals 4 minus e to the 2t. It looks very much like it's going to cross the x-axis at 4. So the area of the region we're talking about is between the x-axis, the y-axis, and the curve. And it looks like it's going to be a and b as 0 and 4. But of course, we can check that by solving it properly. So we can find for definite where it crosses the x-axis by putting y equal to 0. And when we do that, we get 4 minus e to the 2t equals 0. Hence, e to the 2t is 4. And square rooting e to the t is equal to 2. Hence, x, which is 3e to the t minus 2, is the same as 3 times 2 take 2, which indeed does equal 4. So we've got 0 and 4 for our limits for a and b. But as we are integrating parametrically, we will need to convert the limits into values of t. So when x equals 0, we have 3e to the t minus 2 equal to 0. Hence, e to the t is 2/3, which means that t is the natural logarithm of 2/3, ln 2/3. So when x is 0, t is log of 2/3. And when x is 4, as we saw before, e to the t is 2, so t is ln 2. So we've worked out what the limits are. So turning 0 and 4 for x into t values, we know that y equals 4 minus e to the 2t. So finally, we just need an expression for dx. So dx by dt is 3e to the t, and hence dx is 3e to the t dt. So now we're going to put it all together. Our limits are log of 2/3 and log of 2. Y is equal to 4 minus e to the 2t, and dx is equal to 3e to the t dt. So multiplying 4 minus e to the 2t by 3e to the t gives us 12e to the t minus 3e to the 3t. E to the 3t because we're adding our indices, 2t and t. When we integrate it, we get 12e to the t minus e to the 3t. And then we substitute in our limits, 12e to the ln 2 minus e to the 3 ln 2. Take away 12e to the ln 2/3 minus e to the 3 ln 2/3. So 12e to the ln 2 minus e to the ln 8, because we make it ln 2 cubed. And similarly at the end, we've got e to the ln 8/27, which is 2/3 cubed. 12e to the ln 2 is the same as 12 times 2, which is 24. E to the ln 8 is 8. 12e to the ln 2/3 is the same as 2/3 of 12, which is 8. And e to the ln 8/27 is 8/27. And then simplifying that, we get 224 over 27. For the area. Now we can actually check it using standard integration by combining y and x together to get rid of the parameter. So if x equals 3e to the t minus 2, then rearranging that, e to the t is equal to x plus 2 over 3. And then we can substitute e to the t equals x plus 2 over 3 into our expression for y. So y becomes 4 minus the square of x plus 2 over 3. So if we square x plus 2 over 3 and make it into a single fraction, we end up with y equals 32 minus x squared minus 4x over 9. So we're going to integrate y with respect to x between 0 and 4. We don't need to change the limits because we're doing this in terms of x. So y is 1/9 of 32 minus x squared minus 4x. When we integrate that, we get 32x minus 1/3 x cubed minus 2x squared, which gives us 1/9 of 128 minus 64/3 minus 32. When we substitute 4 in there, and 0 when we substitute 0 in there, which gives us the same answer as before, 224/27. And now we're going to look at a trigonometric example. Find the area of the region enclosed by the curve defined parametrically as x equals 5 cos theta, y equals 3 sine theta. So when we plot the graph of this, we get an ellipse. It crosses the x-axis at -5 and +5, and it crosses the y-axis at -3 and +3. Now if we integrated this between 0 and 2 pi for theta, that would be 1 full revolution. That would give us an answer of 0 because the top half would cancel with the bottom half. So instead I'm going to integrate it between 0 and 5 for x, and we'll work out what the values of theta are for that, and that will give us 1/4 of the area. So then whatever we get, we can multiply it by 4 for the total area. So when x is 0, that means that 5 cos theta equals 0, hence cos theta equals 0, and theta is pi over 2. And when x is 5, 5 cos theta is 5, cos theta is 1, and theta is 0. So when x is 0, theta is pi over 2, and when x is 5, theta is 0. We also need an expression for dx. So when x equals 5 cos theta, dx by d theta is -5 sine theta, and dx is -5 sine theta d theta. So we want to integrate y with respect to x between 0 and 5 for x. So using our limits, that means we're integrating between pi over 2 and 0. Y is 3 sine theta, and dx is -5 sine theta d theta. So again, simplifying, tidying up, we get -15 sine squared theta d theta. And what we can do here is we can change the -15 to a +15 and swap the limits to get it as we would like it to look. So we're integrating 15 sine squared theta d theta between limits of 0 and pi over 2. As we've seen before, the integral of sine squared theta with respect to theta is a half theta minus a quarter sine 2 theta. And then when we substitute pi over 2 into that, we get pi over 4 minus a quarter sine pi, and a quarter sine pi is 0. And when we substitute 0 into that, we get 0 minus a quarter sine 0, which is 0. So our final answer is 15 pi over 4, and then when we multiply that by 4, we get an area of 15 pi.